Hello, and welcome to this presentation on graphical solutions of linear simultaneous equations. That's equations of the form y equals mx plus c. It is assumed you've seen a previous presentation relating to the plotting of linear lines of the form y equals mx plus c, as the knowledge and techniques from that presentation underpins the work we're going to review here. It is also assumed you can transpose given equations, as we will need to do so within this work. To solve the linear simultaneous equations graphically, we're going to plot the individual equations on a graph, find the intercept of the equations, and then read off the associated x value and the associated y value. Example 1L, we're asked to solve the following linear simultaneous equations graphically. We're given two equations. The first one here, y minus 2x is equal to 2, and the second equation, 3y plus x is equal to 20. The first thing we need to do is to rearrange the equations in the form of y equals mx plus c. Considering the first equation given in the example, I'm simply going to add 2x to both sides of the equation to form this equation, the y is equal to 2 plus 2x. Just notice that's written in the form of y is equal to c plus mx in this case. But that does not make any difference to the way we undertake the calculation. So I've called this rearranged equation here, equation 1. Considering the second equation given, the 3y plus x is equal to 20, I need to rearrange this to make y the subject. So first of all, I'm going to subtract x from both sides of the equation to get 3y is equal to 20 minus x. And I'm going to divide throughout by 3. So I end up with y is equal to 20 divided by 3 as a fraction minus the x divided by 3. If you want to write that in decimals, you can. Y is equal to 6.6 recurring. Notice the dot at the top of the number there means recurring, minus 0.3 recurring times x. As I do not have a recurring symbol on my word processor, I've simply written that as y is equal to 6.6667 and minus 0.3334 times x. I'll call that equation 2. Again, that's written in the form of y is equal to c plus mx. We're going to plot the equations between the range of x is equal to 0 and x is equal to 3. In some questions, the range over which to plot the values of x is stated. In other questions, you'll find it's not stated. So one way of finding the range is to sketch the equation and then determine the range of x values to use in the solution. Basically, we're looking for where the two lines intersect because that's the solution of the equation. So we want a range of x that accommodates that intercept. Referring to the previous work we look at for solving equations graphically, we have to plot the points. So we're given the x values. I'm using 0, 1 and 3 here. From the previous presentation, we know we only need 2 points to plot a straight line, but we usually plot 3 or more just to make sure we have the accuracy of the line. Considering the equation 1 shown above, we simply put the values of x into the equation and work out the associated values of y. If you're unsure on how to calculate the y values, I refer you to the previous presentation on plotting linear lines. And using equation 2 from above, again we calculate the values of y for the given values of x. Again, I'm adding lots of 6s and 3s here to show that it's a recurring number. Just a brief overview of how to sketch the equations given and so determine the range of x over which to plot the graphs. Given equation 1 here, don't forget we said that was in the form of y is equal to c plus mx in this case. It's still the equation of a straight line, but it's not written in the conventional form of y equals mx plus c. So from our previous presentation, we know the m relates to the gradient and we know the c relates to the intercept. So on my graph here, the intercept is at 2, so I have a point here. And if the gradient is 2, that means we have a rise of 2 in a distance of 1. So this would be the distance of 1 and the rise of 2. So my first line I could sketch will be something like this. Reviewing the equation 2, y is equal to 6.6 recurring, that's the intercept. and the gradient in this case is a negative 0.3 recurring. So I can plot that now on my graph. So 6.6 recurring is the intercept with the y-axis, and the gradient is negative a third. So that means we have a rise of 1 in a distance of 3. So in this particular case, that point will be somewhere here. So from our sketch of the two lines, we can clearly see the intercept or the solution occurs here. So plotting the range of x values from 0 to 3, as we did on the previous slide, is a reasonable range in which to find the solution to the equations. But that's an insight into how we can sketch the equations given and then estimate the range of x values to use in the solution. Example 1L continued. Here's the graphical solution of the simultaneous equations. Here's the first equation given, the y is equal to 2 plus 2x, drawn here. And here's the second equation, the y is equal to 20 divided by 3 minus x divided by 3 in fraction form, drawn here. And we can see that our intercept occurs here. So reading on the x-axis, we can find that x is equal to 2, shown here. And reading on the y-axis, we find that y is equal to 6, shown here. So our solution of the equations are x equal to 2 and y is equal to 6. So what you've seen here in example 1L is the basic approach we'll use to solve all the problems in this presentation, where we're trying to find the solution of two linear simultaneous equations using the graphical method. Where further complexities can occur is in the rearrangement of the equations given, and also when the questions are contextualized. And later in the presentation we'll consider contextualized examples of solving simultaneous equations graphically. Example 1L continued. This is the analytical solution to the problem shown on the previous page. We covered analytical techniques in a previous presentation, and I'm using the elimination process in this particular slide. The main essence of this presentation is to solve the equations graphically, but for those of you interested in the analytical solution, in this process we're going to subtract equation 2 from equation 1. What you'll find is because the coefficients associated with the y terms are both 1 in this case, when we subtract the equations, we eliminate y from the equation and we leave ourselves with a simple equation in terms of x, which can be solved. And x is shown to be 2 here by the rearrangement. And back substituting the value of x I've chosen into equation 1 here, we can find the value of y. If you want more information on the analytical solution methods, then please refer to a separate presentation. But basically we have now checked the graphical solution shown on the previous slide with this analytical solution. Graphical solutions of linear simultaneous equations continued. In example 2L, we've got a contextualized problem. And these are more difficult because now you have to extract the information from the question and form the simultaneous equations before you can solve them graphically. So in this example, we have two machine operators producing the same assemblies. Their total output is 440 units in 1 week. If the ratio of their individual outputs is 6:5, we've got to determine the number of assemblies per week that each operator produces. So in this particular question, I'm going to use notation of operator A and operator B. You can use X and Y if you want to. So I'm denoting operator A as producing the greater output of the two operators. Step 1, I'm going to generate my two equations from the given data. First of all, we can note from the information given that the total output is 440 units per week. So output from operator A added to the output from operator B must total 440 units in the week. I've called that equation 1. To form the second equation, we need to consider the ratio of their individual outputs, which is given as 6:5. So from the information given, operator A produces 6 units for every 5 units from operator B. As a mathematical equation, the ratio of output from operator A to operator B is equal to 6 to 5. And I'll call that equation 2. So those are two simultaneous equations generated from the information given. Example 2L continued. I just repeated equations 1 and 2 for convenience. So in step 2, we need to rearrange the simultaneous equations so that they can be solved. So rearranging equation 1 above, this equation here, to make A the subject, I'm simply going to subtract B from both sides. So the equation becomes A is equal to 440 minus B. And I've called that equation 1A just for reference. Rearranging equation 2 from above, to make A the subject, I will have to multiply both sides by B in this case. So A will equal to 6 divided by 5 times B, or simply 1.2B. 6 divided by 5 is 1.2. I've called that equation 2A. I'd encourage you to start the presentation and just think through for a moment how I've arrived at equations 1A and 2A for your reference. Step 3, we need to plot the equations over a range, and the range given here is B is equal to 0 to B is equal to 300. In this case, we will plot the A on the vertical axis, on the y-axis, and the B on the horizontal axis, the x-axis. And again, we can sketch the equations in order to determine the range of x values, or B values in this case, within which the solution can be found. I'll show you the sketching process on the next slide. So for the moment, given 3 points of B at 0, 150 and 300, we can now calculate the values of A for equation 1A, given on this line here, and the values of A in equation 2A, given here. Again, if we briefly consider how to sketch the lines to find the range of B values to use, note again the equations of form y is equal to C plus mx, in this case, using conventional notation. So our first line, the A is equal to 440 minus B. Notice that's minus 1B, coefficient is 1 there. So the gradient m will be 1. But it's a negative gradient, so we have a negative line. The 440 is the constant c, the intercept with the y-axis. So putting 2 points for equation 1a, 440 on our scale is somewhere there. And we've got a negative line with a 1 in 1 gradient, so that will be here for the second point. So there's a sketch of the line A is equal to 440 minus B, equation 1A. We now take equation 2A, that has an intercept value of 0. Let's put the 0 here, so that's of the form y is equal to mx plus c, so c is 0, and the m in this case is positive 1.2. So our first point will be at 0, 0 for our line, and then our gradient is going to be a rise of 1.2 in a distance of 1. So our second point could be considered as a rise of 120 in a distance of 100. So we could plot the second point somewhere here. So here's our sketch of the two lines, and it's clearly seen that the intercept, or the solution to the problem, is shown to be here. So the range of B values used on the previous slide of 0 to 300 seems reasonable, as within that range we can clearly see we have our solution. Example 2L continued. Here's the graphical solution of the linear simultaneous equations. The first equation, the A is equal to 440 minus B, is plotted on this line here. And the second equation, the A is equal to 1.2B, is plotted on this line here. You can clearly see that the solution to the equations is the intercept shown here. Reading off on the horizontal axis, we can see that the value of B is 200, B shown here. And reading off on the vertical axis, we can see the value of A is 240. 240 shown here. So in summary, operator A produces 240 units per week and operator B produces 200 units per week. As you can see, we've satisfied the initial conditions in that the total output of both operators in a week is 440 units, and the ratio of output between operator A and operator B here is 6:5, again as given in the question. Here are some tutorial questions relating to the solution of linear simultaneous equations using graphical methods. Question 1L, we're given two equations. You have to rearrange both equations in terms of y equals the mx plus c expression. And we're asked to plot the lines between x equal to 0 and x equal to 3. The answers are shown in the right hand side on the square brackets. Question 2L, here again we're given two equations and we're told the range of which to plot the x values. Again, the answers are shown in the brackets on the right hand side. And finally, question 3L, we're given again two equations, but this time we're not told over which range of x to plot the equations. So once you've rearranged the equations, sketched the lines, you should be able to find the range of x over which to plot the equations to find the solution. Answer again is given on the right hand side. I'd encourage you to start the presentation and attempt these questions. Questions 4L through to question 6L are solving simultaneous equations again, but this time we have contextualized questions to attempt. Again, I would strongly encourage you to start the presentation and attempt these questions. The answers are shown in the brackets on the right hand side. The full work solutions to some of these questions are shown on the following slides. Here's the solution to question 1L. We're given the two equations in the question. As previously, we need to rearrange the equations. As I've shown here, it's equation 1. Shown here is equation 2. We're given the range for which to plot the equation in the question from 0 to 3, so I've chosen values of x of 0, 2 and 3, and I've worked out appropriate values of y for equations 1 and 2. Question 1L continued. Here's the graphical solution of the simultaneous equations. I've plotted both equations and here is my intercept. It reads 1 on the horizontal axis, so x is 1, and it reads 2 on the vertical axis, so y is 2. You can always check the solution by putting the values of x and y back into the original equations and seeing if they balance. Question 3L solution. Again, we're given two equations in the question. We're not told in this particular case what range to plot, so you need to rearrange the equations, shown here equation 1 and equation 2, and then sketch the curves as best you can to determine the range of x. Just showing you a slightly different format of equation 1, shown here, where the gradient is 2/3 and the intercept constant is -5/3. And also here for equation 2, where y is equal to x divided by 2 minus 1. So the gradient is a half, or 0.5, and the intercept constant is -1. So I used a range of x values from my sketch between 3 and 6. So I worked out the values of y for equations 1 and 2. On the next slide, I'll show the graphical solution. Let's now consider sketching the equations 1 and 2 to help us determine the range of x values to use in this case. So in equation 1, we can see that the intercept with the y-axis would be -5/3. That's -1.6 recurring. So that's in this region here. The gradient for equation 1 is 2/3, or 0.6 recurring. So that's 0.6 recurring rise in a distance of 1. So there's equation 1 sketched. Now considering equation 2, that's got an intercept constant of -1, so that will be here, and the gradient is 1/2, or a half. So that's a rise of a half in a distance of 1. So the second point will be here. So there's equation 2 sketch, so we can see the intercept is somewhere in this region here. So from the sketch, plotting between 3 and say 5 or 6 would be a reasonable range of x values to use to find a solution. Question 3L, here's the graphical solution for the simultaneous equations. We can see that the intercept is shown to be here, and reading on the horizontal axis, that will be a value of 4, so x is equal to 4, and reading on the vertical axis, the y is equal to 1. So our graphical solution to the problem is x is equal to 4, or y is equal to 1. Finally, question 4L solution. We were given 100 meters of wire and 8 plugs cost £12.40, and 150 meters of wire and 10 plugs cost £18. We've got to find the cost of 1 meter of wire and the cost of a plug. So in this question, I've let W equal to the cost of the wire, and P is equal to the cost of a plug. To generate our equations from the question, to generating the first equation, 100 meters of wire plus 8 plugs is equal to £12.40, and we can rearrange that for P. P is equal to 12.4 minus 100W all divided by 8. I call that equation 1. Notice in equation 1 as it's formed, the W is on the x-axis, the horizontal axis, and the P is on the y-axis, the vertical axis. And the second equation, 150W plus 10P is equal to 18. We can rearrange that equation. P is equal to 18 minus 150W all divided by 10. That's equation 2 here. The range of W I've used in pounds is from 0.05 through to 0.12. And then for equation 1, we can work the values of P in pounds, and equation 2, the values of P in pounds. If you want to sketch the equation to find the range of W values in this particular case, then write in the equation 12.4 minus 100W all divided by 8 as P is equal to 1.55 minus 12.5W, and also equation 2, 18 minus 150W divided by 10 can be written as P is equal to 1.8 minus 15W. That might help if you want to sketch the lines. Question 4L continued. Here's the graphical solution to the simultaneous equations. The intercept occurs in this region here. So reading horizontally, the x value, or the W value in this case, is 0.1. And reading vertically, the P value, the Y value, is equal to 0.3. Reading from the graph, the cost of the wire is 0.1 pounds per meter, or 10 pence per meter, and the cost of a plug is 0.3 pounds, or 30p. For your reference, here's the bibliography used to help generate the presentation. I hope this has been of interest to you, and thank you for viewing.